Welcome to Differentiating Inverses and Compositions. This is Dr. Gilbert Iyabi. These notes are taken from the text Advanced Calculus by Patrick M. Fitzpatrick, 2nd edition. Introduction. Let f be a function from the domain I, the interval I, to the set of real numbers, so a real valued function. Now, in chapter 3, we saw that if I is an interval and the function f is strictly monotone and the image of I under f is j, then the inverse of f from j to r is continuous. A natural question to consider would be the differentiability of f inverse at the point y0, where y0 equals f of x0. Recall that j equals f of I. These two have to work together. So f goes from I to f of I, which is j, and that's a subset of r, and f inverse goes from j back to I. Now, if I use elements, what's going on is this. F maps x0 to f of x0, and we call that f of x0 y0. F inverse starts off at y0 and maps it back to x0, which is f inverse of y0. So that's what we're looking at here. So if f is differentiable at x0, would our f inverse be differentiable at y0? We already know f inverse is continuous. Does that lead to differentiability? And that is what we want to cover in differentiating inverses and composition. So, Theorem 4.2.1. Let I be a neighborhood of x0 and let the function f from I to r be strictly monotone. So we have x0 in I is a neighborhood of x0. Monotonicity of f is given. Next, suppose f is differentiable at the point x0 and the first derivative is not 0 at that point x0. Define j to be the image of I under f. So j equals f of I. Then we can conclude that the inverse function f inverse from j to r is differentiable, as a matter of fact, at the point y0 equals f of x0, and the derivative of f inverse at y0 is just 1 divided by f prime at x0. Interesting. Very, very simple and straightforward. So the first derivative of the inverse at the point y0 is just 1 divided by f prime at x0, where y0 equals f of x0. You must always keep those two together. Let's look at the proof. It's a beautiful proof. Now, from the intermediate value theorem, j is a neighborhood of y0. So we know that I is a neighborhood of x0 and j equals f of I. So j is a neighborhood of y0. Now, for a point y in j, y different from y0, let's define our x to be f inverse of y. Now, how do we come about that? Now, recall that f goes from I to r and f inverse goes from j to r, where we know that j equals f of I. So if we look at it, if I pick any x from I, f of x equals y, and this y is going to be in j. So since f inverse exists, if f of x equals y, I can see that x equals f inverse of y. So we can define this. Again, if I pick a point arbitrarily from j and the point is y, and that's different from my given y0, I'm interested in the differentiability at the point y0. So pick a y that is not y0, and I define my x to be f inverse of y. Again, I've told you why that is feasible. Recall the definition of the first derivative of f at the point x0. Limit as x approaches x0, f of x minus f of x0 divided by x minus x0. So, since I'm interested in the differentiability of f inverse, I'm going to apply the same thing. So, consider limit as y approaches y0, f inverse of y minus f inverse of y0 divided by y minus y0. This is just going to be the first derivative of f inverse at the point y0, according to the definition of first derivative. Now, let's go slowly. What is f inverse of y? F inverse of y is just going to be x, and therefore f inverse of y naught is going to be x naught. What about y and y naught? Well, look at it right here. Y equals f of x and y naught equals f of x naught. So I put all of those together and that gives me limit as y approaches y naught, x minus x naught divided by f of x minus f of x naught. This almost looks close to what we are interested in, except that it's flipped. That is not a problem. I just flip it again. So this can be written as limit as y approaches y naught 1 divided by, now I flip it, f of x minus f of x naught divided by x minus x naught. Observe that this expression is exactly the same as this. But what do I know? By the quotient limit theorem, if I pull my limit to the numerator, I pull my limit to the denominator, this quantity right here is simply f prime at x naught. So this equals limit as y approaches y naught 1 divided by f prime at x naught. In other words, we're saying that, remember, this quantity is f inverse prime at the point y naught. So we're saying that f inverse from j to r is differentiable at the point y naught in j, and the first derivative at the point y naught is nothing but 1 divided by f prime at x naught. And we are done. Now, do not forget, throughout, we are using the fact that f of x equals y from our definition up here. X equals f inverse of y, which means f of x equals y. So, if f is continuous, f is differentiable at the point x naught, f is monotone, I is an interval, then f inverse exists, f inverse is differentiable, f inverse is continuous, and the first derivative is 1 divided by f prime at the point x naught, where y naught equals f of x naught. And that brings us to the end of the proof of Theorem 4.2.1. Now, here's a very simple corollary that goes with that. Let I be an open interval and suppose that the function f from I to r is strictly monotone and differentiable with a non-zero derivative at each point in I. If j equals f of I, then the inverse function is differentiable and the derivative is given as follows. So that is just what we saw in 4.2.1, except that this time around is differentiable with a non-zero derivative at every point x in I. So we can then define f inverse prime at the point x for all x in j. Proof. Since differentiability implies continuity, the function f from I to r is continuous. Now apply Theorem 4.2.1, not 0.2.1, this theorem right here, 4.2.1. At x in j, where your x is given as f of f inverse of x. Recall that this is just going to be x. And f inverse x plays the role of x naught. So plug that in, and we have the intended equation. End of proof. I would leave the fine details of the proof as a simple exercise for serious students. Next, proposition 4.2.3. Let n be a natural number and define g of x to be x raised to the power 1 over n where x is greater than 0. Then the function g from the open interval 0 infinity to r, the set of real numbers, is differentiable and the first derivative is 1 over n x raised to the 1 over n minus 1 for every x strictly greater than 0. Interesting. This almost looks like the power rule for derivatives. You know, if f of x equals x to the n, the first derivative is n x to the n minus 1. Well, we're actually going to use that. Proof. Define f to be the function from the open interval 0 infinity to r, and let it be f of x equals x raised to the power n, where x is greater than 0, n is a natural number. Then, by the definition of g, we see that g is the inverse of f. As I mentioned before, by the power rule of derivatives, the first derivative of f would be n x to the n minus 1, where x is strictly greater than 0. Now we can apply corollary 4.2.2. The first derivative of the inverse equals 1 divided by the first derivative of the function, and the inverse stays inside. Let's apply that. So by corollary 4.2.2, the first derivative of g, which is actually the first derivative of the inverse of f, is 1 divided by the first derivative of f, parentheses, inside, as I mentioned, the inverse of f, which is g of x. But what's the first derivative of f? Is n x to the 1 over n, all of that raised to the n minus 1. Now simplifying that, we get 1 over n x to the 1 over n minus 1 if x is greater than 0. So putting all of that together, what we are simply saying is that if x is greater than 0 and f of x equals x to the r, where r is a rational number, it doesn't matter whether it's an integer or a natural number, as long as it is a rational number, the first derivative of f would simply be rx raised to the r minus 1, and that brings us to the end of the proof of proposition 4.2.3. Now let's talk a little bit about composition and then we would be done. Theorem 4.2.4, the chain rule. Let I be a neighborhood of x0 and suppose that f from I to r is differentiable at x0. Now let's consider j. J is an open interval such that f of I is entirely in j, subset of j. Now suppose that the function g from j to r is differentiable at the point x0. You can delete this second one. Then the composition g composed with f from I to r is differentiable at the point x0, and the first derivative of the composition is g prime at f of x0 times f prime at the point x0. So I differentiate f at x0 times the derivative of g at f of x0. Let's look at the proposition that goes with that very easily. Proposition 4.2.5, for a rational number r, define h of x to be x raised to the power r for x greater than 0. Then the function h from the open interval 0 infinity to r is differentiable, and the first derivative is rx raised to the r minus 1 for x greater than 0. We already mentioned this when we looked at proposition 4.2.3. So the detailed write-up for the proof of proposition 4.2.5 is left as a simple exercise for serious students. Actually, the proof is found in the text Advanced Calculus by Patrick M. Fitzpatrick, and you can look at it. It's a very easy, straightforward proof, very close to what we did in 4.2.3. And this brings us to the end of section 4.2, differentiating inverses and compositions. Thank you, and I'll see you in 4.3. God bless you.